Neutron stars are cosmic enigmas that defy everything we know about the nature of matter. To put their staggering density into perspective, a single sugar cube's worth of neutron star material would weigh billions of tons here on Earth. These remnants of stellar explosions are so extreme that they push the boundaries of physics, bending the rules of reality itself. In this video, we're diving into 35 bizarre facts about neutron stars, facts so astonishing they could easily be mistaken for science fiction. From their mind-bending origins in the fiery deaths of massive stars to their unthinkable gravitational forces, neutron stars are a testament to the universe's capacity for the extraordinary. So, let's begin this journey by uncovering how these celestial wonders are forged in the chaos of a supernova explosion. When a star reaches the end of its life, it doesn't go quietly. Take a star at least 8 times more massive than our Sun. Once it burns through its nuclear fuel, it's destined for one of the most spectacular events in the cosmos. The star's core can no longer support its own weight, and it collapses. This implosion triggers an explosion so powerful it can outshine an entire galaxy for a brief moment, a supernova. This cosmic fireworks show doesn't just destroy, it creates. The explosion scatters heavier elements like iron, gold, and carbon across the universe, the very building blocks of planets and life itself. But what's left behind is just as fascinating. The star's core, now crushed under unimaginable pressure, transforms into something extraordinary, a neutron star. Imagine taking the mass of a star and squeezing it into a sphere no wider than a small city, about 12 miles across. This mind-boggling compression results in an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. Neutron stars are the universe's ultimate leftovers, born from chaos and forged under extreme conditions. And as we'll see next, their density is just the beginning of what makes them so bizarre and captivating. If you thought the weight of a mountain was impressive, prepare to have your mind completely blown. A single teaspoon of neutron star material weighs billions of tons. Let that sink in for a moment. To put it in perspective, that's like taking Mount Everest or even an entire city and squeezing it down into a tiny scoop you could hold in your hand. This staggering density is the result of matter being compressed to levels that are almost impossible to comprehend. Inside a neutron star, protons and electrons are forced together under unimaginable pressure, merging to form neutrons. This process creates a material so dense that it defies everything we know about the physical world. Think of it this way. If you could somehow scoop up a teaspoon of neutron star material and bring it back to Earth, it would instantly sink through the planet's surface, cutting through rock and metal like a hot knife through butter. The sheer weight of it would be incomparable to anything we've ever encountered. But this mind-bending density isn't just a quirky fact. It's a direct result of the extreme conditions within neutron stars, where gravity is so intense that it warps the very fabric of matter. And speaking of gravity, this brings us to the next jaw-dropping characteristic of neutron stars: their gravitational pull, which is so powerful it can distort space and time in ways that sound like something straight out of science fiction. Imagine dropping a feather on Earth. It floats gently down, taking its time to reach the ground. Now picture that same feather on the surface of a neutron star. In this scenario, it wouldn't just fall. It would slam into the surface at a mind-bending speed, almost instantly reaching a significant fraction of the speed of light. That's the kind of unimaginable gravity we're talking about, around 200 billion times stronger than what we experience on Earth. This extreme gravitational pull isn't just a wild statistic, it warps the very fabric of spacetime itself. Light passing near a neutron star doesn't travel in a straight line but bends dramatically, a phenomenon known as gravitational lensing. It's like looking through a cosmic magnifying glass, where the star's gravity distorts the light from objects behind it, creating surreal visual effects. But the gravity of neutron stars isn't just a theoretical curiosity. It shapes their behavior in profound ways, influencing everything from their structure to the bizarre phenomena they produce. And speaking of bizarre phenomena, the next fact about neutron stars will leave you spinning literally. These cosmic powerhouses don't just sit still, they rotate at speeds that defy comprehension. Now let's dive into one of the most jaw-dropping features of neutron stars, their incredible speed. These cosmic powerhouses can spin hundreds of times every single second. To put that into perspective, imagine a ballerina pulling in their arms during a spin, causing them to twirl faster and faster. That's essentially what happens to a neutron star when its massive progenitor star collapses. As the star's core contracts, its rotation speeds up dramatically due to the conservation of angular momentum. It's like nature's way of saying, hold on tight. This rapid spinning isn't just a fascinating quirk. It's the key to some of the most mesmerizing phenomena in the universe. Take pulsars, for example. These are neutron stars that send out beams of radiation as they spin, acting like cosmic lighthouses. Every time one of those beams sweeps past Earth, we detect a pulse of energy, sometimes with clockwork precision. It's almost as if the universe is sending us a signal, reminding us of the incredible forces at work in the cosmos. And just when you think neutron stars can't get any more fascinating, there's another layer to their mystery. Beyond their dizzying spins, these objects emit signals that have puzzled scientists for decades. What could these enigmatic messages from the depths of space be telling us? Now, let's turn our gaze toward one of the most fascinating behaviors of neutron stars, their ability to act like cosmic lighthouses. These aren't just any neutron stars, they're called pulsars. Picture this: as a pulsar spins, it sends out beams of intense radiation from its magnetic poles. If these beams happen to sweep across Earth, we detect them as regular pulses of light or radio waves. It's like watching a lighthouse beam rotate, except this one is traveling across the vastness of space at incredible speeds. One of the most famous examples is the Crab pulsar, located in the heart of the Crab Nebula. This pulsar spins about 30 times every second, sending out pulses of radiation with remarkable precision. Astronomers have used pulsars like this to test theories of gravity, map the structure of the Milky Way, and even search for gravitational waves. Their predictable pulses make them some of the most reliable clocks in the universe. But what makes these pulsars even more intriguing is the sheer energy behind their beams. The radiation they emit can be so intense that it outshines entire galaxies, even though the pulsar itself is only about the size of a city. It's a reminder of just how extreme the universe can be, packing so much power into such a small package. And if you're wondering what fuels this incredible phenomenon, it all comes down to the neutron stars' intense magnetic fields. Speaking of which, that's where our next fact takes us, into the realm of magnetic fields so strong they defy imagination. Neutron stars aren't just dense, they're also home to some of the most powerful magnetic fields in the universe. To put this into perspective, Earth's magnetic field, which guides compasses and protects us from solar radiation, is downright feeble compared to what neutron stars possess. These cosmic powerhouses boast magnetic fields that can reach strengths trillions of times greater than our planet's. That's not just impressive, it's almost incomprehensible. So, how do neutron stars generate such extreme magnetism? It all comes down to their rapid rotation and mind-boggling density. When a massive star collapses into a neutron star, its core compresses into a sphere no larger than a city, yet it retains much of the star's original magnetic field. As the core spins sometimes hundreds of times per second, the magnetic field becomes concentrated and amplified to staggering levels. Think of it like a figure skater pulling in their arms to spin faster, but on a cosmic scale with unimaginable energy. These intense magnetic fields have profound effects. In some cases, they give rise to magnetars, a special type of neutron star that's essentially the universe's ultimate magnet. Magnetars are so magnetic that if one were halfway between Earth and the Moon, it could erase the data on every credit card on our planet. Their magnetic fields are strong enough to warp the very fabric of space-time and produce bursts of X-rays and gamma rays visible across the cosmos. But here's where it gets even more intriguing. These magnetic fields aren't just static. They interact with the neutron star's surface and surroundings in ways that can create sudden, dramatic changes. One of these mysterious phenomena is something called a glitch, where the star's rotation suddenly speeds up. And that's just the beginning of the bizarre behavior these cosmic giants can exhibit. Now let's dive into one of the most baffling behaviors of neutron stars, glitches. Picture a cosmic speedster spinning with incredible precision, and then suddenly, it revs up just a tiny bit faster. This strange phenomenon is exactly what happens during a neutron star glitch, where the star's rotation unexpectedly accelerates. Scientists believe these glitches occur because of the star's unique internal makeup. Imagine a neutron star's crust as a rigid shell, but beneath it lies a superfluid core that flows without resistance. When the crust and core momentarily decouple and then reconnect, it creates a sudden jolt, speeding up the star's spin. These glitches might seem minor, but they're like cosmic breadcrumbs, offering clues about the mysterious inner workings of neutron stars. And speaking of their surfaces, did you know that neutron stars might even have mountains? Picture a star so dense that its surface is almost perfectly smooth, shaped into a near-flawless sphere by the crushing force of its own gravity. Now, imagine that even in this extreme environment, tiny imperfections can form little bumps on the surface that scientists call mountains. But don't think of these mountains as towering peaks. On a neutron star, they're incredibly small, measuring just a few millimeters high. That's like a grain of sand on a basketball. Yet, despite their size, these minuscule deformations are anything but insignificant. The immense gravity of neutron stars makes even these tiny bumps incredibly massive, packing the weight of an entire mountain range into a space smaller than a fingernail. What's truly mind-blowing is that these tiny mountains can actually produce ripples in the fabric of space-time, known as gravitational waves. When neutron stars rotate, these imperfections create disturbances that radiate out into the universe. Advanced observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory, are sensitive enough to detect these ripples, giving us a way to listen to the vibrations of these distant stars. It's a reminder that even the smallest details in the cosmos can have profound effects on our understanding of the universe. And speaking of neutron stars making waves, there's an even more dramatic event involving these stellar remnants, one where they crash into each other in a spectacular collision. When two neutron stars collide, the universe itself seems to shudder. These incredibly dense objects, each containing more mass than our Sun packed into a city-sized sphere, spiral toward each other at astonishing speeds. As they merge, they unleash a cosmic symphony, a phenomenon known as gravitational waves. These are ripples in the fabric of space-time, predicted by Einstein over a century ago, and they carry the story of the universe's most violent events across vast distances. The collision doesn't just produce these waves, it's also a cosmic forge, creating heavy elements like gold and platinum. In a single cataclysmic event, neutron stars transform raw matter into treasures that eventually find their way into planets, jewelry, and even our own technology. One of the most groundbreaking moments in science occurred in August 2017, when astronomers detected gravitational waves from a neutron star merger for the first time. This discovery not only confirmed Einstein's theory, but also opened a new window into understanding how the universe builds its most complex materials. Speaking of extreme phenomena, let's turn our attention to another astonishing aspect of neutron stars: their unimaginable temperatures. When a neutron star is born, it's not just dense and small, it's blazingly hot. In fact, at the moment of their formation, neutron stars reach temperatures in the trillions of degrees. that's hotter than the core of the Sun by a staggering margin. But where does all this heat come from? It's a combination of two powerful processes, the decay of neutrons and the release of gravitational energy. As the star's core collapses during a supernova, the immense gravitational forces compress matter to unimaginable densities, converting that energy into heat. Over millions of years, neutron stars gradually cool, but even as they age, they remain incredibly hot, often measuring in the millions of degrees. This intense heat isn't just a byproduct of their formation, it's a window into the extreme physics at play. The temperatures inside neutron stars are so extreme that they can't be replicated in any lab on Earth. In a way, they act as natural cosmic laboratories, allowing scientists to study the behavior of matter under conditions that defy our everyday understanding. And speaking of cosmic laboratories, this leads us to our next mind-blowing fact. Neutron stars aren't just hot, they're also incredible testing grounds for the laws of physics, pushing the boundaries of what we know about the universe. Neutron stars are more than just cosmic oddities. They're natural laboratories beyond anything we could ever create on Earth. Imagine the kind of pressure that crushes atoms into a sea of neutrons, leaving behind a dense core where the rules of physics as we know them are pushed to their limits. These extreme conditions make neutron stars the perfect testing ground for some of the most profound theories in science. Quantum mechanics, which governs the behavior of particles on the tiniest scales, and general relativity, which explains the fabric of space-time itself, both play out in ways that are impossible to observe anywhere else. When scientists study neutron stars, they're essentially peering into the universe's most extreme physics experiment, unlocking secrets about the very nature of matter and gravity. But here's something even more intriguing. The surface of a neutron star might not be as smooth as you'd think. In fact, scientists believe these stars could have solid crusts, almost like a cosmic shell encasing their unimaginable interiors. This leads us to the next mind-bending fact. Neutron stars might just have landscapes complete with mountains and valleys, albeit on a scale that defies anything we're familiar with. A neutron star isn't just a dense ball of chaos, it's a marvel of cosmic architecture. Picture this: beneath its surface lies an outer layer that's anything but ordinary. This solid crust, just a few hundred meters thick, is made of atomic nuclei packed tightly into a crystalline lattice. Think of it like a diamond, but one forged from the remnants of a supernova and under unimaginable pressure. These nuclei are squeezed together so tightly that they form a structure so dense it's almost incomprehensible. And yet, this crust isn't static, it's floating. Beneath it lies a superfluid core, a bizarre state of matter where particles flow without friction, creating a strange and dynamic interplay. The crust isn't just sitting there, it's constantly influenced by the swirling, frictionless interior, making neutron stars some of the most complex objects in the universe. But that's not all. This intricate interior has another surprising trick up its sleeve. The intense forces at play can cause neutron stars to emit powerful X-rays, a phenomenon so extraordinary it deserves its own spotlight. Neutron stars are not just cosmic curiosities, they're also powerful X-ray factories. These ultra-dense remnants of supernovas are incredibly hot, with surface temperatures reaching millions of degrees. Combined with their intense magnetic fields, this heat causes neutron stars to emit X-rays at staggering levels. To study these emissions, scientists rely on X-ray telescopes like the Chandra Observatory, which has captured breathtaking images of neutron stars in action. These images aren't just beautiful, they're packed with information, revealing details about the star's surface, its magnetic field, and even the turbulent environment around it. By analyzing these X-rays, astronomers can piece together the life story of a neutron star, from its explosive birth to its current state. Speaking of surfaces, did you know that some neutron stars might even have atmospheres? That's right, we'll explore that possibility next. Here's a smooth and engaging continuation of the script based on the outlined segment. Even though neutron stars are incredibly dense and compact, they manage to have something as delicate as an atmosphere. Picture this, an atmosphere so thin it's only a few centimeters deep, barely thicker than the length of your finger. These ultra-thin layers are often made of hydrogen or helium, the lightest elements in the universe. But don't let their size fool you. These wispy atmospheres play a crucial role in how we observe neutron stars from Earth. The atmosphere acts like a filter, shaping the way light and X-rays escape from the star's surface. Without it, the emissions would look entirely different. The hydrogen or helium atoms interact with the intense radiation, bending and scattering it in ways that create the unique patterns we detect with telescopes. This is why neutron stars don't just appear as faint dots in the sky. They shine with distinct signatures that tell us about their composition and behavior. But neutron stars aren't static. Over time, they can change in surprising ways. For instance, did you know that these cosmic powerhouses can gradually slow down? It's a process that's as fascinating as it is complex, and it's all tied to their incredible magnetic fields and the energy they emit. Let's dive into that next. As neutron stars age, they don't just sit quietly in the cosmos. They slow down like cosmic timekeepers winding down. This gradual loss of rotational energy happens over millions of years, a process driven by two main forces: the emission of electromagnetic radiation and the ripples of gravitational waves. These waves, a result of the star's intense gravitational field, carry energy away from the neutron star, causing its spin to steadily decrease. It's almost as if the universe itself is gently tapping the brakes on these spinning behemoths. But what's even more fascinating is that this slowdown isn't just a quirk of physics, it's a window into the star's life cycle, revealing how these incredibly dense objects evolve over time. And speaking of evolution, could neutron stars also host planets? It's a question that sounds like it's straight out of science fiction, but the answer might surprise you. Did you know that even neutron stars can have their own planets? It might sound like something straight out of science fiction, but these bizarre worlds known as pulsar planets are very real. The first pulsar planets were discovered in the early 1990s orbiting a neutron star called Pulsar B 1257+12. This discovery was groundbreaking because it proved that planets could form or survive in the most extreme environments imaginable. But how do these planets come to exist? One theory suggests that they form from the debris left behind after a supernova explosion. When a massive star collapses into a neutron star, it doesn't just vanish, it leaves behind a swirling cloud of material. Over time, this debris can clump together, forming planets. Another possibility is that these planets are captured by the neutron star's immense gravity, pulled in from elsewhere in the galaxy. Either way, these planets are unlike anything in our solar system. Imagine a world where the sky is lit by a pulsar instead of a sun, flashing with bursts of energy every few milliseconds. And speaking of bursts, neutron stars aren't just home to strange planets, they can also unleash some of the most powerful explosions in the universe. Among the most cataclysmic events in the cosmos are gamma-ray bursts, sudden, intense flashes of gamma radiation that can outshine entire galaxies. And guess what? Neutron stars, especially a special class known as Magnetars, are often the culprits behind these mind-boggling explosions. These bursts are so powerful that they can release more energy in a few seconds than our sun will emit over its entire 10 billion-year lifespan. But how does something so small, barely the size of a city, produce such a colossal blast? The answer lies in their extreme magnetic fields and internal stresses. In magnetars, the magnetic fields are so intense that they can literally twist and snap, releasing vast amounts of energy in a process called magnetic reconnection. Another possibility is starquakes, violent shifts in the star's crust caused by the immense pressure building up inside. These events are like cosmic earthquakes, but on a scale that's almost impossible to fathom. What's truly fascinating is that these bursts are not just spectacular fireworks, they're windows into the bizarre physics of neutron stars, revealing the extreme conditions that govern their behavior. Speaking of extreme conditions, let's take a closer look at what might be hiding beneath the surface of these dense stars. Could neutron stars have cores made of something even stranger than neutrons? That's where the next mystery begins. Deep within the heart of a neutron star, where pressures are so immense they defy comprehension, scientists theorize that something even stranger than neutrons may exist, a core of free quarks. Quarks, the fundamental building blocks of matter, are usually tightly bound together in protons and neutrons. But under the crushing gravity of a neutron star, it's possible that neutrons themselves might break apart, giving rise to a quark-gluon plasma, an exotic state of matter where quarks roam freely. This idea, while still theoretical, could explain some of the bizarre behaviors observed in neutron stars, like their inexplicable density and heat. It's a mind-bending concept, matter stripped down to its most basic components, existing in a form we've never directly observed. And speaking of bending, neutron stars don't just push the limits of matter, they also twist the very fabric of time itself. Now, let's dive into one of the most mind-bending effects of neutron stars, their ability to warp time itself. Thanks to their unimaginably strong gravitational fields, neutron stars create a phenomenon where time slows down near their surfaces. This is no science fiction, it's a direct prediction of Einstein's theory of general relativity, which tells us that gravity can bend the fabric of space-time. The stronger the gravity, the more time stretches and slows. Near a neutron star, where gravity is millions of times stronger than Earth's, this effect becomes extreme. To put it in perspective, if you could somehow hover just above the surface of a neutron star and watch a clock back on Earth, you'd see it ticking much faster than your own. This surreal effect, known as gravitational time dilation, has actually been observed in pulsar timing experiments, where the precise flashes of pulsars are used to measure how their gravity alters the flow of time. It's a stunning confirmation of Einstein's predictions and a testament to how neutron stars push the boundaries of our understanding of the universe. And speaking of pushing boundaries, let's shift our focus to an intriguing question. Could neutron stars have rings? Here's the next part of the script based on your outline segment. It turns out neutron stars aren't always solitary, isolated objects. Some of them are actually adorned with rings like cosmic jewelry. These rings are made up of debris, often material that was flung out during the star's explosive birth or captured from a neighboring star. Picture Saturn's iconic rings, but on a much smaller, denser, and more extreme scale. What's fascinating is that these rings aren't just for show, they emit radiation, which scientists can study to uncover secrets about the neutron star's past. By analyzing this radiation, researchers can piece together the story of how the star formed and what it's been through over millions or even billions of years. But that's not all. These rings also serve as a reminder of the chaotic and dynamic nature of the universe. Neutron stars, despite their extreme density, aren't static. They interact with their surroundings in ways that continue to surprise us. And speaking of surprises, this leads us to another mind-blowing fact about neutron stars: their ability to act as some of the most precise cosmic clocks in the universe. Neutron stars aren't just cosmic oddities, they're also some of the most precise timekeepers in the universe. Pulsars, a type of neutron star, emit beams of radiation that sweep across space like a lighthouse, creating regular pulses. These pulses are so incredibly consistent that they rival even the most advanced atomic clocks here on Earth. Scientists use pulsars as cosmic metronomes, leveraging their rhythmic beats to test fundamental theories like Einstein's general relativity. By observing how the timing of these pulses changes in the presence of massive objects, researchers can study the effects of gravity in extreme conditions. But the utility of pulsars doesn't stop there. Their predictable pulses have even been used as interstellar GPS, helping spacecraft navigate the vast expanse of space with remarkable accuracy. It's astonishing to think that these dense remnants of dead stars can serve as both cosmic laboratories and celestial guides. And speaking of neutron stars' incredible properties, their magnetic fields are equally mind-boggling, so powerful they can trigger massive explosions. Among the most extreme phenomena in the universe are the magnetic explosions that occur on magnetars, a special breed of neutron stars. These cosmic powerhouses possess magnetic fields trillions of times stronger than Earth's, making them the most magnetic objects known. But what happens when such an unimaginable force becomes unstable? The result is a cataclysmic event called a starquake. As the immense magnetic field lines twist and strain under the star's immense gravitational pressure, they eventually snap like overstretched rubber bands. When this happens, it unleashes a burst of energy so intense that it can outshine entire galaxies for a fraction of a second. These explosions, known as gamma-ray flares, release more energy in a single moment than our Sun could produce in thousands of years. It's a reminder of just how dynamic and volatile neutron stars can be. And speaking of energy, this brings us to another fascinating aspect of these cosmic giants: their ability to emit radio waves, which we'll explore next. Now, let's zoom in on one of the most fascinating features of neutron stars: their ability to emit radio waves. Imagine a cosmic lighthouse in the depths of space, sending out beams of energy that sweep across the universe. That's essentially what a pulsar does. These rapidly rotating neutron stars emit intense beams of radio waves from their magnetic poles. As they spin, these beams sweep through space like a celestial searchlight. When one of those beams points toward Earth, we can detect it as a regular pulse of radio waves, hence the name pulsar. This phenomenon has been a game-changer for astronomers. Since the first pulsar was discovered in 1967, these radio wave emissions have helped scientists identify thousands of neutron stars. By studying the timing and patterns of these pulses, we've been able to learn incredible details about their rotation speeds, magnetic fields, and even their environments. It's like listening to the heartbeat of the universe, each pulse revealing a new piece of the puzzle. But here's where it gets even more intriguing. These radio wave emissions aren't just a way to find neutron stars, they're also a window into their internal structure. By analyzing the signals, scientists can make educated guesses about what's happening deep inside these dense stellar remnants. And that leads us to a tantalizing question: could neutron stars have solid cores? It's a possibility that challenges everything we thought we knew about these extreme objects, and it's the perfect segue into our next fact. For all their crushing density and mind-bending physics, neutron stars might just harbor a secret that sounds like something out of a sci-fi novel. Their cores could be solid. Yes, you heard that right. Beneath layers of unimaginably dense matter, these cosmic powerhouses might have cores that are not just super dense but potentially solid. But what could they be made of? Theories suggest exotic states of matter, like hyperons particles that are essentially heavier versions of protons and neutrons, or even Bose-Einstein condensates, a strange state where particles behave as a single quantum entity. These materials are so bizarre, they don't exist anywhere in the universe under normal conditions. This solid core could have profound effects on the star's behavior, influencing how it rotates and even the gravitational waves it emits. Imagine a spinning top with a dense, solid center. It would wobble and vibrate differently than a hollow one, giving astronomers clues about what's happening deep inside. And speaking of deep, did you know neutron stars can also blast out neutrinos, the ghostly particles that barely interact with anything? That's where our next fact takes us, into the realm of these elusive cosmic messengers. Have you ever heard of particles so elusive they can pass through an entire planet without bumping into a single atom? Neutron stars are cosmic factories for these ghostly travelers known as neutrinos. These nearly massless particles are produced in staggering quantities within the crushing cores of neutron stars. especially during the dramatic moments of their formation. Neutrinos are so insubstantial that they barely interact with matter, allowing them to zip through space and even through Earth itself almost unnoticed. But their role in the life of a neutron star is anything but insignificant. As they escape into the void, they carry away a tremendous amount of energy, acting like a cosmic cooling system for these incredibly dense remnants of stellar explosions. Over millions of years, this steady stream of neutrinos helps neutron stars gradually lose their heat, transitioning from searing hot remnants to cooler, more stable objects. But the mysteries of neutron stars don't stop there. What happens when these exotic objects begin to lose not just heat, but their incredibly powerful magnetic fields? That's where our next fact takes us into the fascinating process of magnetic field decay, a phenomenon that shapes the evolution of these stellar oddities in ways we're still trying to fully understand. Neutron stars are often thought of as eternal cosmic dynamos, but even their incredible magnetic fields aren't immune to the passage of time. Over millions of years, these fields can weaken in a process called magnetic field decay. Now, you might wonder why this matters. Well, the magnetic field of a neutron star is what powers its ability to emit intense beams of radiation and govern its rapid rotation. As the field decays, the star's emissions become less energetic and its spin gradually slows down. It's like a cosmic clock winding down, but on a timescale far beyond human comprehension. This decay also impacts the star's interaction with its surroundings, altering how it interacts with nearby matter or even other stars. It's a reminder that even the most extreme objects in the universe are subject to change. And speaking of extreme, neutron stars aren't just fading powerhouses, they're also capable of something downright astonishing. Up next, we'll explore how these stars can act as cosmic particle accelerators, blasting particles to speeds that put even our most advanced Earth-based machines to shame. Neutron stars aren't just dense remnants of supernovae, they're also some of the most powerful particle accelerators in the universe. Thanks to their incredibly strong magnetic fields, which can be trillions of times stronger than Earth's, these stars can hurl particles to nearly the speed of light. This acceleration isn't just a cosmic spectacle, it's a key process that generates high-energy radiation, including X-rays and gamma rays. As these particles collide with the surrounding environment, they create a dazzling display of energy that can be detected across vast distances. This phenomenon not only illuminates the star itself, but also shapes the space around it, influencing the behavior of nearby matter and even other celestial objects. What's even more fascinating is how this relates to the magnetic structure of neutron stars. These stars don't just have static magnetic fields, they can have magnetic poles that wander over time, shifting and altering the way energy is emitted. This wandering creates a dynamic and unpredictable environment, adding another layer of mystery to these already enigmatic objects. Did you know that even neutron stars, these cosmic powerhouses with immense magnetic fields, can experience a kind of cosmic restlessness? It's called polar wandering, and it's exactly what it sounds like. The magnetic poles of a neutron star can shift positions over time. Imagine Earth's North Pole deciding to take a stroll across the planet. That's essentially what happens here, but on a scale that's far more extreme. This wandering isn't just a curious quirk, it has real consequences for how these stars behave and how we observe them from Earth. When the magnetic poles move, it changes the way the neutron star emits radiation. For pulsars, which are neutron stars that beam light and radio waves from their poles, this shift can make their pulses appear irregular or even vanish entirely from our view. It's like trying to spot a lighthouse whose beam keeps changing direction. Sometimes it's visible, and sometimes it isn't. This phenomenon makes studying pulsars even more challenging, as astronomers have to account for the possibility that these stars might be playing cosmic hide and seek with us. But this isn't the only way neutron stars keep us on our toes. their restless nature also ties into another incredible phenomenon, one that ripples through the fabric of space-time itself. Neutron stars aren't just cosmic heavyweights, they're also masterful creators of gravitational waves. These ripples in space-time, first predicted by Einstein's theory of general relativity, are generated by some of the most extreme events involving neutron stars. When a neutron star experiences a glitch, a sudden change in its rotation, or undergoes a starquake, a massive shift in its crust, it sends out gravitational waves that ripple across the universe. Even more dramatic are the waves produced when two neutron stars collide in a binary merger, an event so powerful it can momentarily outshine entire galaxies. These waves aren't just fascinating cosmic signals, they're tools for scientists to probe the secrets of neutron stars and test the very fabric of gravity itself. It's like having a new set of eyes to observe the universe. Speaking of observing the unseen, there's another mind-bending aspect of neutron stars that pushes the boundaries of physics: the possibility that their interiors might be filled with superfluid matter, a state of matter so bizarre it defies everything we know about how fluids behave. Deep within the heart of a neutron star lies one of the most bizarre and intriguing substances in the universe: superfluid neutrons. Picture a fluid so perfect that it flows without a hint of friction, defying everything we know about how matter behaves. This isn't science fiction, it's the reality inside neutron stars. Scientists believe that the incredible densities and pressures at the core force neutrons into this superfluid state, where they move in perfect harmony, unhindered by resistance. This frictionless flow has dramatic effects on the star's behavior. As the superfluid spins, it creates tiny whirlpools called vortices, which twist and interact with the star's crust. These vortices can influence the neutron star's rotation, sometimes causing sudden changes in its spin rate, a phenomenon known as a glitch. Imagine a cosmic ballet of swirling currents, invisible yet powerful enough to reshape the star's motion across light years of space. But the strangeness doesn't end there. The superfluid interior also plays a role in how neutron stars emit energy, setting the stage for an even more dazzling spectacle. And speaking of dazzling, the next fact dives into how these celestial powerhouses can light up the cosmos in ways that boggle the mind. Now, let's shed some light, quite literally, on another fascinating aspect of neutron stars. These incredibly dense remnants of supernova don't just sit quietly in the cosmos. They can actually emit visible light, often in the form of pulsating beams that sweep across space like celestial lighthouses. This light isn't just random. It's produced by the neutron star's intense magnetic fields and rapid rotation. As the star spins, its magnetic field accelerates charged particles to near light speeds, causing them to emit radiation, including visible light in concentrated beams. When these beams align with Earth, we observe them as pulses, giving rise to the term pulsars. But not all neutron stars are pulsars. Some emit a steady glow, while others flicker in patterns so precise they rival atomic clocks. This dynamic interplay of rotation and magnetism not only illuminates the neutron star itself, but also offers clues about its internal structure and the extreme physics at play. Speaking of magnetic fields, did you know they can do more than just generate light? Stay tuned, because our next fact will reveal how these fields can twist and warp in ways that defy imagination. Now, let's explore a phenomenon that turns neutron stars into cosmic powerhouses of chaos. Imagine the magnetic fields of these stars, trillions of times stronger than Earth's, becoming twisted and tangled like a cosmic rubber band stretched to its limit. These fields aren't just static, they're dynamic, writhing with energy. When the tension becomes too much, the fields snap, releasing explosive bursts of energy. This process is thought to power some of the most dramatic events in the universe, magnetar flares. These flares are so intense that, for a fleeting moment, a magnetar can outshine an entire galaxy. It's like a cosmic lightning strike, but on a scale that's almost incomprehensible. What's even more fascinating is that this twisting and snapping of magnetic fields isn't just destructive. It's also a crucial mechanism that shapes the environment around neutron stars. And speaking of shaping the cosmos, that leads us to the next incredible fact. Neutron stars can act as cosmic beacons, guiding our understanding of the universe in ways that are both profound and unexpected. Picture this, a spinning lighthouse in the vast ocean of space, its beam cutting through the darkness like a cosmic signal. That's essentially what a pulsar is, a neutron star acting as a celestial beacon. These dense remnants of stellar explosions emit regular, incredibly precise pulses of radiation, ranging from radio waves to X-rays and gamma rays. It's like a cosmic metronome, ticking with such accuracy that astronomers have even used pulsars to test Einstein's theory of general relativity. What makes these pulses so extraordinary is their consistency. Some pulsars rotate hundreds of times per second, while others take a few seconds per spin, but their rhythm is so reliable that scientists can use them as natural cosmic clocks. In fact, these pulses have been instrumental in mapping the structure of the Milky Way. By measuring the time it takes for these signals to reach Earth and how they're affected by interstellar gas and magnetic fields, astronomers can piece together a detailed map of our galaxy's sprawling arms and mysterious voids. But pulsars aren't just tools for navigation, they're also windows into the extreme physics of our universe. The energy they emit can help us study the properties of interstellar space, revealing how matter and radiation interact across unimaginable distances. And speaking of extreme physics, while pulsars dazzle us with their precise pulses, there's something even more mind-bending about neutron stars, their magnetic fields. These aren't just strong, they're among the most intense forces in the cosmos. Next up, let's explore how these magnetic fields can twist, snap, and reconnect in ways that challenge our understanding of the universe. When it comes to neutron stars, their magnetic fields are nothing short of mind-blowing. These fields are so intense that they can actually snap and reconnect in a process called magnetic reconnection. Picture this, a sudden release of energy so colossal that it's like the universe itself is rewiring its circuitry. This isn't just a small spark, it's a cosmic explosion of energy that can trigger some of the most dramatic events in the cosmos, like gamma-ray bursts and X-ray flares. Gamma-ray bursts are among the most energetic phenomena in the universe, and X-ray flares can light up space with bursts of high-energy radiation. It's like the neutron star is firing off cosmic fireworks, but on a scale that's almost impossible to comprehend. And here's the kicker, this magnetic reconnection doesn't just happen once. It's a recurring event, constantly reshaping the environment around these celestial powerhouses. But that's not all. The energy released during these events doesn't just vanish into the void. It plays a crucial role in shaping the universe around us, influencing everything from star formation to the distribution of cosmic rays. Speaking of cosmic rays, that leads us to yet another astonishing fact about these stellar remnants, a revelation that will leave you in awe of their sheer power. Now, let's zoom in on one of the most mind-blowing facts about neutron stars, their ability to launch cosmic rays across the universe. These dense stellar remnants don't just sit quietly in space, they're cosmic particle accelerators on a colossal scale. When particles get caught in the intense magnetic fields of a neutron star, they're whipped up to speeds approaching that of light, transforming into cosmic rays. These high-energy particles then race through the cosmos, cutting across galaxies and even reaching us here on Earth. But what does this mean for the universe as a whole? These cosmic rays from neutron stars are part of the invisible tapestry of background radiation that fills space. They contribute to the energy soup that scientists study to understand the workings of the cosmos. It's like neutron stars are constantly adding ingredients to this cosmic recipe, helping to shape the environment in which stars, planets, and even life itself can form. What's truly fascinating is how this ties into the bigger picture of neutron star research. By studying these cosmic rays, scientists can unlock secrets about the extreme conditions around neutron stars and even the origins of the universe itself. It's a reminder that these bizarre objects aren't just isolated curiosities, they're key players in the grand story of the cosmos. And speaking of their role in the universe, let's take a closer look at why neutron star research is so crucial and what it reveals about the fabric of reality. Neutron stars are more than just cosmic curiosities, they're windows into the deepest mysteries of the universe. By studying these dense stellar remnants, scientists gain invaluable insights into the fundamental laws of physics, from the behavior of matter under extreme pressure to the nature of gravity itself. Imagine squeezing the mass of our Sun into a sphere the size of a city. Neutron stars are the ultimate testbed for theories that govern the extremes of space and time. One of the most groundbreaking contributions of neutron star research lies in its role in understanding the origins of heavy elements. It's believed that the cataclysmic collisions of neutron stars, known as kilonovas, are responsible for seeding the universe with elements like gold and platinum. These rare events, detected through both light and gravitational waves, have reshaped our understanding of how the cosmos builds the materials essential for planets and even life itself. But the discoveries don't stop there. Neutron stars also offer clues about the universe's evolution. Their magnetic fields, pulsations, and interactions with their surroundings provide a unique laboratory for testing theories about the early universe and the forces that shaped it. With advancements in gravitational wave astronomy, we're now able to detect ripples in space-time caused by neutron star collisions, opening up a new era of cosmic exploration. Looking ahead, the potential for future discoveries is staggering. Could there be even more exotic types of neutron stars waiting to be found? What secrets might they hold about the behavior of matter under conditions we can scarcely replicate on Earth? As our tools and technologies continue to evolve, neutron stars will undoubtedly remain at the forefront of astrophysical research, guiding us toward answers to questions we're only beginning to ask. Neutron stars are a testament to the universe's ability to defy imagination. As we've explored these 35 astonishing facts, one thing becomes abundantly clear. Neutron stars are not just dense remnants of stellar explosions. They are cosmic enigmas that push the boundaries of physics. From their mind-boggling density, where a single teaspoon of material would weigh billions of tons, to their unimaginable gravitational pull that distorts the very fabric of space-time, these stellar relics are nature's ultimate laboratories. They challenge our understanding of matter, energy, and the laws that govern the cosmos, offering scientists a glimpse into conditions that are impossible to replicate on Earth. But beyond their scientific significance, neutron stars inspire awe and wonder. They remind us that the universe is far stranger and more fascinating than we can often comprehend. These bizarre objects, born from the fiery deaths of massive stars, continue to captivate astronomers and laypeople alike with their extreme properties and mysterious behaviors. Whether it's their ability to spin hundreds of times per second or their role as cosmic lighthouses emitting beams of radiation, neutron stars are a constant source of discovery and intrigue. As we wrap up this journey through the wild world of neutron stars, it's impossible not to feel a sense of curiosity about what else lies out there in the vast expanse of space. These stellar remnants are just one piece of the cosmic puzzle, and there are countless other mysteries waiting to be uncovered. What do you think about these incredible objects? Do you find neutron stars as fascinating as we do? Share your thoughts in the comments below. We'd love to hear your perspective. If you've enjoyed this deep dive into the bizarre and awe-inspiring realm of neutron stars, don't forget to subscribe and hit that notification bell. We're constantly exploring the wonders of the universe, from black holes to exoplanets and beyond, and we'd love for you to join us on this cosmic adventure. Until next time, keep looking up and stay curious because the universe is full of surprises waiting to be discovered.